Okay, so for this problem, you have a cart of what we'll call mass big M, and we'll call this the initial state. So we'll just say the momentum initially, and then we'll call this the final state where it's the momentum in the next snapshot. So if you have a guy hopping on here, and we'll just represent him as mass little m, and he's hopping on here at a speed of v naught. What's going to happen is you'll have the guy on the cart both moving at a final speed, which we will call v. Okay? So the conservation of momentum is a law where momentum must be conserved in the system, and we'll just say conservation of p for short. And the conservation of momentum says p initial is equal to p final. Okay, so how do we define the initial state of momentum? Well, you have the momentum of the first of the box and the momentum of the man. So what we'll say is um, the momentum, the velocity of big M times big M plus the initial velocity of the man and his mass is the initial momentum. And this will equal the final momentum, which will be some velocity v times big M plus little m, or the combinations of mass. And this is the same exact thing as saying v of m total. Okay. So in order to do this, or sorry, not v of m total, it'll be v times m total. Okay, so if this makes sense so far, that you have two separate masses adding together to get a combined mass with some combined velocity. So what we could say is the block of mass m is, in physics terms, is at rest. And at rest is just lingo for the v of the big mass is equal to 0. It has no speed. So essentially what you'll be getting is the first term goes to 0, so you'll just have v naught m is equal to v times m total. Okay? And I'll just put the 0 term here just to show you that it goes to 0. So essentially what happens is v is just going to be v naught m, little m, divided by m total, which is the same thing as v naught m over big M plus little m. And that will be the final speed at which they are both going. Alrighty.